Welcome. My name is Steve Holmes. I'm a video application engineer from Tektronix. Today we're going to look at troubleshooting MPEG in a cable TV network. When we test, it's nice to have a guideline or a measurement tool to test to. In the MPEG world, we have a measurement guideline known as ETSI TR 101290, or simply 101290. TR 101290 is broken into three priorities. We have the first priority, which has things like sync, PAT, PMT, continuity count errors. Second priority, which gets into more program decodability things like PCRs, CRCs, and FEC type problems. And then the third priority, which gets into things like the electronic program guide for off-air recordings. One of the things that always seems to come up when looking at MPEG is a little bit of confusion about MPEG 2, DVB, ATSC, and the like. Everything is MPEG 2 based. So if you are dealing with a DVB stream, it is actually MPEG 2 with all of the DVB tables laid on top of MPEG 2. If we're dealing with ATSC, it is actually ATSC tables laid on top of MPEG 2 tables. So everything we deal with is MPEG 2 based with PAT and PMT type tables in it, and then the particular standard sitting on top of that. When we look at TR 101290 and look at the different priorities on the right-hand side, you can see that the priorities are listed down with all of the different parts in them. Priority 1 is what we consider things that are required for decodability or basic monitoring. Basically, it's what is needed for a decoder or a receiver to be able to lock up and sync on a stream. Everything in priority 2 then gets into program decodability within that stream that you've locked onto. Priority 3 then is all of the application-dependent pieces, things like PSIP for an off-air monitoring and things like that. Also, ATSC and SCTE have come up with other characterizations for doing monitoring. These are really, really good types of monitoring protocols, but I personally always fall back to TR 101290 for doing troubleshooting when one of these other error conditions has caught an error. If we take a closer look at the first priority in TR 101290, it is listed down in priority of importance. Error 1.1, TS sync, is stating whether or not you even have a stream to lock onto. 1.2 is looking at sync byte errors. You have synchronization of the stream, but you're losing occasional sync bytes out of the MPEG packets. This is something that's going to lead to further error degregations pretty quick. 1.3 is primarily typically looking at the program allocation timing. How often am I putting in a PAT table into the stream? 1.4, the continuity count error, is probably one of the most important ones in the entire monitoring chain. 1.4, continuity count, is actually looking at dropped MPEG packets. So every time you get a continuity count error, it is a packet that is completely missing and not presentable to the customer on the screen. 1.5, the PMT error, is very much like the PAT error, primarily looking at how often am I putting a PMT table into the stream. 1.6 is kind of an older error condition that in most conditions today we actually have to disable because of unique conditions in the stream, like commercial insertion, ad errors and things, that looks at whether or not a table that has been signaled is in the stream at least once a second or more often. And if you think about how often we put a commercial in, or if you're looking at music choice, how often we're changing the video slate, that actually causes, both of those conditions cause a 1.6 error. So in a lot of cases, 1.6 ends up getting disabled because of those items. If we look at priority 2 out of TR 101-290, the first one in priority 2 is the transport sync error. The transport sync error looks at whether or not a previous chain to what you're looking at, typically an RF FEC overflow error in a satellite feed or in the actual RF QAM layer. So when you get a 2.1 error, it's generally trying to tell you you have other errors due to the RF FEC overflow. 2.1 looks at the individual CRCs in the packets. 2.3 looks at how often I'm putting a PCR in the stream, not necessarily the accuracy of that 27 megahertz clock. 2.4 is the one that actually looks at the accuracy of the clock, and that's the one that's most important in 2.1. 2.5 looks at the presentation timestamps. How often am I sending the presentation timestamp packets? And then 2.6 is verifying that if you are scrambling, that you are putting the proper information for the decoder to be able to descramble the streams at a later point in time. Priority 3 gets into some unique issues in that you may have a DVB stream that you're looking at if you're looking at a direct satellite feed prior to coming into your system, or if you're looking at off-air streams coming in before being placed on the cable system. And there are a variety of tables that make up each one of those individual systems. And depending on where you set your analyzer can parse out those tables individually on either a DVB or an ATSC stream and completely look at all of those tables. If you look at a typical screen on the MTM400, we have a monitoring screen and a monitoring page we call FlexView, because it allows you to place what is most important to you onto a single screen. You can place 4 items onto the screen that you choose to turn around and monitor. So in this case, in the upper left-hand corner, we're looking at the total bandwidth and the programs that are actually being inserted into the transport stream. The top right corner, we're actually decoding thumbnails of the individual programs that are going by. In the bottom left-hand corner, we're actually looking at the individual TR 101-290 alarms. And then one of the screens that I like the best in the bottom right is what is an error now and what was an error more than 1 second ago. So that bottom right-hand screen is a very, very handy screen to look at to see at a glance, do I have any errors right now? Or if I've had a phone call, what were the errors that I just had on this particular stream? You can look at the individual items a number of different ways. This is a program-centric view where you can actually go into a stream, look at the programs, look at the makeup inside of the transport stream, and look at each one of the programs, and look at the contents, the video, the audio PIDs, inside of each one of the streams, and see if there are any errors. In this case, the video PID in program 2 has had an error, and simply clicking on that PID would bring up an error list of exactly what happened at what point in time. You can also click on the test tab right next to the program tab, and you can get an exploded view of all of the tests. And you can look at the errors from a test-centric point of view and go down the tree on the left-hand side, click on the particular piece that's either in error now or wasn't in error, and get a report of exactly when that error happened and what the error was that happened. One of the key pieces and challenges to monitoring when we're looking at this stuff is really what makes the phone ring. Things that actually are customer centric, things that are customer reporting. When you look at the MPEG stream, there's a lot of things we test in MPEG that may or may not directly make the phone ring, but is technically out of spec. So things that actually make the phone ring are things like absolute loss of signal, the loss of a program, picture breaking up, or audio breaking up. A program map table being 20 milliseconds over the limit will not make the phone ring. It is technically non-compliant, but the services going out to your customers are going to be absolutely perfect. So we need to be able to look at things. Things that we look at are not absolutely black and white. It's like looking at video. We don't reject video that is at 101 IRE instead of exactly 100 IRE. Well, the same thing goes for MPEG monitoring. There are certain things that can be tolerated and certain things that cannot. So one of the challenges to MPEG monitoring is being able to know what are things that are binary, basically just pure good, bad. They have to be there in the stream. What things have acceptable working windows, and what are those particular working windows for my system? So looking at the network only will not give you everything you need to know. You need to be able to look at both the network perspective and the MPEG perspective. Let's face it, your customers are actually watching MPEG video. They aren't watching an IP flow. So things that are binary alarms that we look at in going through this stuff are things like sync byte errors, sync byte missing. Continuity count errors, as I said before, is one of the biggest pieces because every time you get a continuity count error, you are going to get errors on the screen, almost guaranteed. Transport error flags. Some point in the network on a satellite feed that you're getting from some other service provider has gone into error, but now the errors are appearing in the middle of your network. That transport errors flag will help you look back and actually tell you where the error is coming from. And then basically any table that is missing for more than 1 second. If you have a table that has gone for too long, set-top box will error out and they will shut off on the service. Things that are adjustable, that are capable of moving out from what the absolute parameters are the table timing issues. Like the PAT table should be coming in at 100 milliseconds or less. The PMT should be coming in at 400 milliseconds or less. The PCR should be coming in every 100 milliseconds or more often. The PTS at every 700 milliseconds or more often. A lot of those tables can move quite a ways out of their range that's listed in the standard for what you're watching and not affect service. The PCRs themselves are supposed to be at plus or minus 100 milliseconds. And the movement beyond that, depending on what it looks like, could very easily not cause any service degradation at all. Today we've got very, very good phase lock loops in the set-top boxes that are capable of handling a lot of PCR jitter and PCR inaccuracies. If we look at the network from the MPEG stream from a network perspective, we can look at the GigE layer and be monitoring several aspects and basically all flows on a GigE pipe and look at several aspects of that GigE pipe in parallel. We can be looking at all of the streams for transport stream sync byte error. We can be looking at all of the streams to make sure there's no continuity errors in them. We can actually look at the MDI delay factor to verify the buffer modeling looks good, the PIT, which is the packet interarrival time, to verify that we don't have any microbursts sitting in there, and then also be able to look at the individual bit rates of each one of the flows to verify that we aren't looking at something or have more information going through our switch than what we think we do, so that we won't get into an issue of oversubscribing a switch port. In looking at the GigE PIT and MDI delay factor screens, those screens will turn around and give you an indication of how well the IP network is actually managing the individual MPEG packets and whether you've got excessive delays that might exceed a buffer somewhere else in the network. So when I unbuffer that MPEG pack of those 7 MPEG packets in the one IP packet and have to put them out as individual MPEG packets, this screen will allow you to see what the buffering and what the pack actually looks like and whether or not you have a switch that is starting to get into trouble or not. If you start having individual spikes, timing spikes, it's a good indication that you possibly have a switch or some other piece of your network that is getting overloaded and you are having network delay issues. These network delay issues where you're separating MPEG packets out may end up causing other errors down the stream if you do not have enough buffer to buffer out that much delay and put out the MPEG packets, and actually could cause other MPEG errors themselves. Looking at different parts of a network and being able to do cross-layer analysis can be very beneficial. In this case, we are actually looking at the MPEG PCRs for the stream and actually looking at the packet interarrival time below that, doing cross-correlation between, do I have any network errors that are actually feeding through to the MPEG layer? Am I taking hits or timing anomalies on the IP layer that actually show up as anomalies in the video layer in the form of PCR hits? Or do I have PCR anomalies that are falling on top of acceptable PCR anomalies that are falling on top of acceptable IP anomalies that when they coincide with each other, the end network error happens because of the two coinciding with each other. So being able to overlay and do cross-layer analysis can be a very important troubleshooting tool when looking at things that are a little difficult to find when you're having some of those elusive errors. If we kind of look at a block diagram of a typical cable network, on the left-hand side, we've got the master head end. In the middle, we've got a sub-head end. On the far right-hand side, we've got the QAM feeds going out to the individual homes. Across the bottom, we have a number of different monitoring probes, looking at IP layer and actually looking at the QAM layer. If we overlay the error, the TR-101-290 error chart with this particular stream, we can look at the effect of the errors and where those errors most likely are coming from. If all of a sudden we take 6 continuity count errors at one time because of the 7-to-1 IP pack, the chances are incredibly high that that error is actually coming out of someplace within your IP domain because of the 6 errors at a crack. If all of a sudden you took a very large number of errors, but you also had the 2.1 error indicator going off at the same exact time, the 2.1 error indicator is trying to tell you that it is not your network. It is a feed coming into your network. So in this case, if it was the IP monitors that went off, it would be telling you that it is coming in from your satellite feed, that you're having an issue coming in from the satellite feed, that the RFFEC is overflowing for whatever reason coming in off of your satellite feeds. If you ended up having the error only off of your QAM monitors and the two IP monitors had no errors for that same service, that would indicate that the network is okay and the problem is actually within the QAM itself. So being able to look across multiple probes for the same service or have a monitoring network that is actually looking across those individual probes for those and do the correlation for you is an invaluable troubleshooting tool and will lead you to the fault resolution much quicker. If, for instance, though, you had a single continuity error and you were taking onesies, twosies as continuity errors, you know you're dropping packets, you know the phone's going to be ringing if it's not already ringing, but that error indication is telling you that it is not coming from within your IP network because you have 7 packets within the IP network. So this is actually indicating that someplace over off of your IP feed coming in, it's actually on an ASI prior to encapsulation. So this is either an ASI feed off of a satellite IRD or off of an ASI feed of an individual encoder coming in. But it's a ASI type issue prior to IP encapsulation because of the one error at a time. If, for example, we had a PCR inaccuracy error here, which is quite often called PCR jitter, but it's actually inaccuracy of the timestamps. Now, this error is actually coming from some video source. The chances of your network itself causing this is pretty slim without causing other issues. The majority of the issues that this come from are either your satellite provider, could come from a ASI to IP converter that is also a rate shaper that has gotten sick. Individual encodes are actually bad content coming in from someone. The next thing you need to kind of look at is what does this error actually look like? So if you graph out the error, certain PCR inaccuracies are immediate issues. Certain PCR inaccuracies are just trying to indicate that you have problems that are going to be looming if it gets much worse. If you happen to have a PCR inaccuracy that looks pretty much like this does, where you have a slow loping signal that's rising fairly slowly, then all of a sudden drops immediately back to another value and then slowly creeps up again, that immediate drop is going to be a definite issue for the set-top boxes. You're asking the phase lock loop and the decoder to lock to a given value, then instantaneously change to another point in time and relock and continue on without giving any hits to the service. The chances are that every time this thing resets, the phase lock loop is going to have to re-zero itself and relock and start over again. But if the changes are slow in nature, this particular PCR is technically non-compliant, it's out of spec, but the individual change from PCR point to the next PCR point is a fairly slow rate of change. The DPLLs in the set-top boxes can actually track that to a fairly large extent and be able to work through those individual phase lock changes and be able to come up with an accurate 27 megahertz clock off of that. This is probably an indication of a problem that is going to be coming, but it's not an immediate fire. This will not typically create the immediate phone ring issue like the previous slide would, but it's something that you are going to have to eventually work on and find out what's causing this, because it's probably going to get worse as time goes on. If we happen to have a program allocation table error, a PAT error, and you expand the PAT error and it comes up with the PAT timer alarm, the chances are pretty good that this is not going to cause a customer affecting issue. It's another one of the alarms that you want to be mindful of and see, is it something that's sliding in my network, or is this just where my network happens to be sitting? If you're looking at an alarm and you're looking for 100 milliseconds as the base for this alarm, and it's coming in just under 300 milliseconds, the chances are very, very great that there's going to be absolutely no issues throughout your network. If your network is sitting here and this is where it is constant happy and this is where you've always been, then probably you just want to move your alarm monitoring threshold above that point and say, okay, we're going to monitor by exception. If anything moves out from this point, we want to be notified. But if it was at one point within the 100 milliseconds and is now slid up to here, this would be a problem of something that will be looming in the future. So you have to make some determinations on some of these things. But as it now sits, it will not cause any errors as far as customer service. It's, again, technically non-compliant, but not service affecting yet. So in summary, in looking at all of these different errors, we need to be able to look at the individual program analysis, be able to look at PCR, look at bandwidth, look at tables, look at the transport layer, both from an IP perspective as well as the MPEG perspective, because most of the errors will end up in the MPEG domain and can actually be tracked back to another domain, either IP, RF, or some other source from within the IP domain by just looking at the individual errors. You need to think of summarizing and looking at the characteristics of these errors. If you've got monitors at multiple head ends and all of the head ends get the same exact error, the chances are then it's coming out of the master head end. But if only one head end has that error, the other head ends off of the same ring and off the same feed do not have the same error, the chances are then you're looking at a localized error that's just in that one head end. So being able to quickly walk from monitoring point to monitoring point to monitoring point quickly, or have a piece of software like VQNet that lays over the top of your network and looks at all of these points and summarizes all that data to give you some error indications is invaluable and can help you troubleshoot and analyze things down to a single point of error very, very quickly. Then for the individual troubleshooting, to have detailed analysis, to be able to look at the protocol syntax, be able to look at continuity counts. Are they onesies, twosies? Are they coming in as groups? And to have the knowledge yourself when you're tasked with fixing these things, to be able to look at the individual errors and say, okay, I'm getting single errors at a time. Okay, that's got to be prior to IP encapsulation. Or I'm getting errors in groups of 5 to 7 at a time. That's going to be in the IP domain. Then looking at PCR analysis and thinking of PCR analysis a little bit in terms of what does a set-top box have to do with looking at this data? And can a set-top box track from point to point, or am I having wide radical swings that would cause an issue? Also need to have a wide range of different types of network interfaces. We get services from ETSI sources, from other IP sources, from QAM sources, from satellite sources, ASI sources, to have a wide range of interfaces to be able to look at all of this stuff and to have a real-time OS that gets in there in your individual monitoring probes, so you don't end up with issues from the monitoring probes themselves getting in and screwing your readings up. In summary, we'd like to be able to look at things as compliance to the MPEG 2 standard, or look at them in each one of the individual standards, to be able to look at it as DC2, DigiCipher 2, DVB, or ATSC, to be able to read the DVB or ATSC tables, to be able to have simple identification errors, to know what makes the phone ring and what doesn't, what are binary alarms, what are the alarms that we can actually move around and slide and look at, to have a network monitoring system that sits on top of this and correlates all of this data for us and actually helps us out, to have the VQ net sitting on top of this and look at all of this and pull all of those data points together to point you to the individual area that you need to look at, to have individual detailed analysis of a problem when you go to troubleshoot it, to look at the protocol and syntax at a given point, to look at the continuity errors and be able to determine, are they coming in one at a time, two at a time, so it's prior to IP encapsulation, or am I getting those groups of errors in 5 or 6 at a time that are looking at IP-only errors because of the grouping of those errors, to be able to look at data rates of the transport, to see if a service provider has increased their transport stream bit rate coming into you that might cause issues that you have a switch that is now oversubscribed, to look at PCR analysis and look at the detail of the PCR analysis to see, is it something that, yeah, the set-top box can still lock onto, but is going to cause me issues shortly, or, yes, that is so bad that it's going to cause me errors right now and I need to jump on that quickly. To be able to look at the IP traffic measurements and correlate the IP issues back to the MPEG layer and do cross-layer analysis, to be able to isolate problems that if I'm looking at one particular monitoring point and I look at another monitoring point and another head end, do they both have the error or not? If they both have errors, the chances are it's coming in from the master head end. If only one subhead end has an error, the chances are that the errors are localized to that particular subhead end. We would like to thank you for your time today. I hope this presentation has helped out and helped you to be able to monitor and look at your network as you go forward. If you would like any more information, please contact Tektronix and we'd be more than happy to help you out with any of your monitoring needs that you have.